Hello, and welcome to a tour of our poster, number 173, at the SCEC 2020 Annual Conference. Here I, Elizabeth Berg, a PhD candidate at the University of Utah, present our joint MCMC inversion of Rayleigh wave phase velocity, ellipticity, and receiver functions. Southern California shear velocity model expanding to the shallower and deeper crust. This work is in collaboration with Professor Fan-Chi Lin, Professor Vera Schultz-Pelcom, PhD student Kostas Gogas, Dr. Hongwei Chiu, and Professor Amir Alam. Our poster begins with a few key points from our abstract. We present a new shear velocity model of Southern California with sensitivity from the near surface into the upper mantle, including to MOHO depths. We use expanded H/V and phase velocity datasets to build off of our previously published studies and incorporate azimuthally corrected receiver functions to avoid bias. We perform MCMC joint inversion at each station to leverage complementary sensitivity of our datasets and quantify model uncertainty. Next, we discuss Rayleigh wave ellipticity, or H/V ratios, as determined by University of Utah PhD student Kostas Gogas. We show H/V in log 10 space at 3 seconds, 6 seconds, 10 seconds, 16, and 24-second periods. We can see higher H/V ratios in the Ventura Basin, Central Valley Basin, LA, and Salton Trough. We also see lower H/V ratios in the Sierra Nevada and in the Peninsula ranges. With increasing period, we see overall lower H/V ratios as our sensitivity moves to below the basins. Next, we briefly discuss phase velocities, published by Dr. Hongwei Chiu, currently a postdoc at Rice University. We show phase velocity maps at 3.5, 6, 10, and 15-second periods. We see low phase velocities in the Central Valley, Ventura, and LA basins, as well as in the Salton Trough. We see higher phase velocities in the Sierra Nevada and Peninsula ranges. See Chiu et al. Published in JGR Solid Earth in 2019 for details. To obtain longer period phase velocity measurements, we use Helmholtz tomography. Helmholtz tomography uses Rayleigh waves from earthquakes. In order to get to lower periods, we use magnitude 3 and larger regional events to supplement our catalog of magnitude 6 and larger teleseisms. Over 700 earthquakes were considered from 2015. We show our phase velocity maps at 15, 24, 30, and 50-second periods. We see lower velocities beneath the Central Valley and then beneath the Sierra Nevada ranges at longer periods. We see lower phase velocities in Salton Trough and fast velocities beneath the Peninsula ranges. Another data set we use is receiver functions as calculated by Professor Vera Schultz-Pelcom at CU Boulder. We will show the receiver function found at station WBS in the Sierra Nevada foothills, along with our MCMC 1D inversion scheme. We are showing VS in the upper 10 kilometers, as well as in the overall upper 100 kilometers. We also show the receiver function, time versus receiver function amplitude, period versus phase velocity, and period versus H/V ratios, along with the data sets associated with each and their uncertainties. Our shear velocity model consists of a top linear layer, a 10 B-spline crustal layer, and a 5 B-spline upper mantle layer. Our whole VS model search space is shown in green dashes. The starting model, which is based on our 2018 model for the crust, and the Lee et al. 2014 model for the MOHO and upper mantle, is shown in red. The forward model of this red shear velocity model is shown in red for the receiver function, phase velocity, and H/V ratios. Posterior models that have relatively good fits for each data set, as determined by the MCMC inversion, are shown in light blue, while the average of this posterior distribution is shown in white, and the average of the posterior is considered to be our final model. We see faster velocities near the surface here, as expected. We now compare MCMC results thus far at each station, interpolated onto the whole map. Note that these results are preliminary, and we are working to include more stations. Once we have stable results from the inversion at each station, we will perform a follow-up joint inversion with our H/V and phase velocity results at each grid point using this interpolated map. We show our VS results from the surface at 0.5, 2, 9, 25, 45, and 65 kilometer depths. We also include our MOHO depths. We see similarities to our previous 2018 study near the surface, including low velocities in the Salton Trough, Central Valley, and Ventura basins. We also see higher velocities in the Peninsula and Sierra Nevada ranges. At greater depths, main observations include a lower velocities in the Eastern California shear zone, fast to slower velocities below the Sierra Nevadas, consistent with previous models and with more recent US Ray models. We also see similarly deeper MOHO in the Sierra Nevadas and in the Peninsula ranges, shallower MOHO beneath the Salton Trough and in the coastal ranges. Thank you for your time and attention.